Thank you. No, this is important. Okay, so this would be part 2 of the lecture. It's probably maybe it's already in one of them, but who cares? Anyway, okay. So what the deal is the oxygen. What did we decide? Negative or positively charged? Negative. Hydrogens were? And if it's all in here also, okay, so you can go over it tonight. Now this thing is spinning around. Is the charges evenly distributed around the water molecule? Do you think there's a more positive side and a more negative side at all times? Okay, we'll come back to that, okay? Now, look at your other model, the little model. What did we decide this was? It's also water. Now, I think this model is better because it gives me more information. First, the first stick and ball model, is the hydrogen the same size as the oxygen? Is that true? No. Is this little model, does it show you that the hydrogens are smaller than the oxygen? So this model is just not quite as lame as that model. Because all models are lame, otherwise we wouldn't use models. We would look at the real thing, okay? Now, this other model has something even cooler about it. Oh, wait, back up. Something they both equally do well is they represent what? The number of atoms, I could say, the formula of water, but there's something more interesting about water. Are the angles, do both models show you the bond angles? Yeah, and so water is at about a 90 degree thing, okay? Now, I want you guys to interact with your models, with the people in the front, turn around with the people in the back, and take turns and see how, hold on, the little model, see how the little model interacts with the other little model, okay? So pass them around, talk to each other, and see how that interacts. Okay, so what is happening here? Let me gather all these models into one hand. So let me steal your models. What is happening? Okay? What is happening? Even when you give it to me, you can see it. Okay, so now, do I have them all? I have them all. Okay, so check this out. This is some what? What do I have in my hand, supposedly? Water. Now, do you think this is a solid, liquid, or gas? Okay, I have some going both ways. If I was to smash it in my hand like this, do you guys think it's a liquid, solid, or a gas? They're moving. Okay, so now if I was to spread them out even more, I can't do 3D very well, it doesn't work. Well, it's that. Okay, so then we're arguing wonderfully about this deal. So first tell me what is happening. What's the deal with how they're arranging themselves? Well, the magnets are a model for reality here. I heard two things I love to hear. One, I heard that they were bonding, hydrogen bonding, somebody said, and that is true. Hydrogen bonds are very weak bonds, but you can see in my model, it is demonstrating hydrogen bonds. Okay, I'm actually holding it from the one on the top, and they're all hanging out. Okay, so that's a strong enough bond to fight gravity, right? And yes, they are really magnets, but it's a model, and it's coming close to representing what happens when that, I heard somebody else say over here, the idea of how, what's the attraction between? The positive and negative. So you can see how your water molecules are lining up positive to negative. Okay, we still haven't solved another problem I've asked you guys. So let me get it a little more complex. Okay. So, is it kind of getting into a crystalline shape? Kind of. Here. There's one stuck in the middle. Okay. You guys see, does it kind of look like a crystalline shape? Do you see that kind of even that? It's like a pentagon. Okay, this one's having some issues. It probably would like some more, wouldn't it? Okay, we have not decided if this is solid or liquid. Are the molecules, at least in the model form, do they seem to be moving? No. Okay, what about density? So let me ask you this. So this right here, when I first look how big it is compared to my hands here. Okay, and then if I smush it and I'm moving them all around together, what was this more dense or less dense than this? So when we were doing this, it was what again? More dense. This is then what? This is less dense. Something's very special about water, because when things are solid, they're typically more dense. Okay, like think of melted glass. Okay, so we decided that this structure was less dense than when I was smashing it around. But what do you guys think? Is this solid or a liquid model? It's solid because of the hydrogen bonds and because of the bond angle, the shape that lines up. And what do we get in between? What do we have pockets of? Air. Okay, so what about ice? What does ice do? Ice does what? What happens when when water freezes? What happens to it? And they form these crystalline shapes. And then what about a lake? Where's the ice? When it freezes, where's the ice on a lake? On the top. If it was like other things and didn't do that, it would form on the bottom because it would be more dense. You would freeze the whole lake. Not good, right? Okay, now, forget about water for a minute. Okay, now I want to compare. Did everybody break down their water? I want a water molecule. Let me have a water molecule. Awesome. And let me steal a methane from somebody over here. Okay, so we decided that the water, you guys look at me, stop for a minute. The water had an uneven distribution of charges, negative side and positive side. Now, did we talk about what the vocabulary word is to describe that? It's in your notes. It's up there. That condition is defined as being what? Polar. Water is polar. That's what it means. The charges are not evenly distributed. Now, what about methane? So methane's just stinky farts. Okay, cows give off lots of this and they're digestive. Okay, so they are never still. They're always moving around. How is the charge on the methane? Is it polar or non-polar?
Non-polar.
Okay, do you see that it's completely what charge all the way around it? Positive. Okay, that's very different. Now, do non-polar things like to hang out? Whose was this? Do non-polar things like to hang out with polar things? No. So methane gas is like ethylene too, ethane. These things are non-polar oils, vegetable oils, fats. So they don't like to hang out with water because of that charge thing. Okay? You would think water would like to line up a little bit, but it's still got enough positive on the other side where it wants to get away. Okay? Now, okay, so I already talked about the hydrogen bonds with you guys. Do you guys remember that? Okay? So again, that's a weak bond, but you guys see this all the time. Don't you guys play with the water when it's on glass or you're hanging out in the bathtub and you could push the water around and then doesn't the water want to get closer to other water droplets? Don't you guys do that? Is your world so busy you guys don't get to play with water droplets? Please, please, everybody play with some water tonight for me, okay? Please, okay? So those are what type of bonds? What's that attraction? Hydrogen bonds, okay? I have plenty of time here, so don't be packing up on me. Okay, moving on. Okay, let's start it. Okay, so back to some ion stuff. So we're talking about sodium chloride being an ionic bond. When they break down, then you have sodium ions in solution and you have chloride ions on solution. And they have charges, okay? So water is everywhere, and water dissolves everything. So there's always ions in water, okay? And that's why water tastes differently. Back to chemicals a little bit. We were talking a little bit about organics. You guys with me? And the idea, you know, of chemicals are kind of chemicals. They all come from nature. Maybe we purify them and play with them more than just using straight leaf extract, for example. Okay? It's the same thing here. When you think of water, the tap water versus your bottled water, it tastes different depending on what's dissolved into it. Not bad stuff, you guys. The source, where it came from. Maybe you don't like tap water because you're tasting a little chlorine. Chlorine are killing the germs. Is that a good thing? Pretty much so, okay? Maybe you're getting fluoride from it also. And then bottled water, you guys need to figure out what you think is a good choice for you. One, I know it's extremely expensive, and you have all that waste, right, of the plastic. And then have you seen the research that's done where, especially if the bottle gets hot, right, the non-polar, the oils, can come out of the plastic and get into your water. Now, I haven't looked it up in a while. I hate the trash of plastic, so I avoid water bottles for that reason. But again, you guys want to make educated choices, and sometimes we're just going out of pure laziness or major convenience. So you got to figure out what's good for you. Okay, so water does dissolve everything. Now, water itself dissolves water. What happens here is the H2O, because they're ions, they can separate too. You can have some water that has more of an acidic taste to it or more of a basic taste to it. You're having OH ions in it versus the H ions. They dissociate, it's called. So you know this scale. What's this scale called? And the H stands for what? Hydrogen. Okay? The amount of hydrogen ions compared to the amount of OH ions. Now, if it has more H's, it's said to be a acid. If it has more OH's, it's said to be basic. Now, you just mess with charges. Are they attracted to other things? Do you think they would work good as soaps, for example? Those OH, that negative charge, pulling stuff off your clothes. Okay, what about acids? The H ion, breaking apart your food in your stomach. So it's the ions that are breaking things apart. Now, I also want you to realize sometimes we think acids are worse than bases. Not so. Both extremes are just as dangerous. For example, oven cleaner. Some really strong vinegar, and that one's not so bad. Does it bother you when you inhale the fumes? It's not good. It's ripping apart your cells. Acid does the same thing also. So strong acids and strong bases are just bad for cells. Well, it depends. Like, it can get into your eyes and kind of burn your eyes. You know what I mean? Just if there's a lot of it in the air there, if it's diffused a lot, it's an acid. So it's about 3 pH. If you put vinegar on something, is it going to clean it? It is. If you guys want, you can just wash your windows with vinegar. It works just as good as Windex, and it is cheaper. Okay, so you should be kind of familiar with this. For sure, this way. The test questions will read things like, is a solution with pH 3, is it an acid or base? It's acid, okay? So you need to be able to use that. Now, what do cells like? What do they want to be around? 7, neutral. We don't want these things ripping us apart. Okay, and then that leads to the last slide, and I'll stop here. What is this phenomena? What's happening in this slide? Acid rain. So our pollution, nitrates, carbon dioxide even, carbon monoxide from our cars, sulfate gets up there, bonds to the H's, makes more acid. Okay, then we have acid rain. But in solution, those H's are attacking things, hurting things. What's happened to these trees? Yeah, they're dying. Okay, what happens to the fish and all the things that live in the water? Okay, so draw a line, and we'll continue here. Thank you guys. You made it through a very long lecture.